Hey robot makers, hope you're having a good day so far. So, do you want to learn about how to build robots using MicroPython and Raspberry Pi Pico? Then this is the show for you. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let me get over to my slides and we can make a bit of a start. So yes, this is all about a new course that I put together. I'll share the link with you very shortly. And it's about how to use MicroPython to build really cool robots. So you can follow along if you want. If you head over to kezrobots.com/learn/micropython_robotics, you can play along for free as well. I'll just show you what that looks like. Just over here on kezrobots.com. So yes, if you head over to free courses, it's currently the #1 course on there. And you can see there we've got everything that you'll be learning in that particular course and the kind of things that you might need to play along. So let's get into it, shall we? So first of all, DC motors. DC motors are an absolute must if you're building robots. It's how robots get from A to B, unless they're a walking robot, of course. So we use it with DC motors all the time. So DC stands for direct current. It's a type of electricity. It's very commonly used. It's the kind of power that you get from a battery, for example. So motors are very simple electronic devices. They turn electrical energy into kinetic energy. So they use some clever magnetism. The electricity flows through the magnets, it spins around a commutator, and we can actually make a wheel turn round with that. So some motors have additional gearing to provide more turning power, torque. So you'll see the little motors that we'll be using a little bit later on. I don't know if, yeah, got one just to hand just here. This little motor here is called an N20 motor, and you can see the silver bit is the actual motor itself, and then this top section that's kind of a brass colour, that is the gearing. Got some fluff on it just there, so you can just see the gearing there. Lots of little cogs that are very clever. Now the more gears that they have, the slower that the motor can actually turn, but the more turning force that it can have, so it'll be a stronger motor. And if you've ever played with a remote control car and the battery's going a bit flat and you put it onto the sort of fast setting, you'll notice that it can't go up inclines very well. But if you turn it to the slow setting, which kind of adjusts the amount of power that's being sent to the motors, it slows them down, but they have a lot more force, so they can actually get up those gradients a little bit easier. So motors can't be powered by microcontrollers directly, so what we can't do is get our motor and kind of plug it directly into our Arduino, or in this case Raspberry Pi Pico. It also goes for microbits. So these typically have a very, very low power, and the power is actually going through the chip itself, the microcontroller. And the thing with motors is they can actually store electricity. So when the wheel's turning round, the wheels don't tend to stop dead. All that magnetic energy goes back through the cables as electricity and actually can damage the microcontroller. So we normally need some kind of board that sits in between the motor and the microcontroller. And that board is the motor driver board, so we can help with this. So one of the very common motor drivers, in fact this powers two of the robots I have behind me, which were sent to me by VM. These ones, these are the L298N motor drivers. They're quite chunky in size, but they can actually take quite a lot of power. So you can put 12 volts into that little pin just there, the ground, and then 5 volts. You can use either 5 or 12. And then these other blue connectors on the sides, this is where you connect the motors up, so you can simply connect up. It doesn't actually matter which orientation you put these, so the plus and minus doesn't matter which way around they go there. You can actually reverse that in code later on if it wasn't spinning the right direction. Then there's also at the very bottom of this whole bunch of little pins just there. So this little bunch of pin headers just here. So they are, you can see on the bottom right there, we have a pin for enabling and disabling the motor, so it's a way of turning it off or on. And then we have IN, which is like input 1, 2, 3 and 4, and then we have the B enable. So we've got two motors that we can possibly drive with this little board. Now when I built the Billy Bass fish project, I actually used 2 of these because I needed 3 motors to be able to control, and I simply just took the little control, the inputs from there. I think I just needed 6 inputs to control 3 motors. So it's a very common board, very powerful, pretty cheap. I've actually got the pricing over here. So I think these are about £2.40 on Amazon to buy. You'll probably get them a bit cheaper if you go somewhere like AliExpress. And this isn't the only game in town, so there are some other boards that we can use. We can use these little ones. This one is called MX1608. I think that's right. 1508, sorry. So you can see that it's very, very small. And it works in pretty much the same way. So you can see on the left-hand side there we've got some pin headers for motor A and motor B. And then on the other side there, kind of hold it upside down, it says we have iron 1, iron 2, iron 3. And they're the inputs again. So from an electrical perspective, these two work exactly the same. But there's also a third type you'll see quite commonly. These are the DRV8833. I think there's lots of variants of this, so you'll see DRV88 then 17, something like that. So this is even smaller. And again, it works in exactly the same way. If we were to look at the pinouts on the back there, get that the right way around, you can see we have inputs 1, 2 and 3. We've got voltage in, ground, and then the outputs, which is like the motor A and B. And we've also got the enabling pins as well. So any of these work great with electronics projects. It just depends on the type of motor that you're using, the amount of power that you want to shove through this. So these all have different kind of ranges of power that you can use with them. But from a software point of view, they work exactly the same. So this is the one that we're using today, this L298N motor driver. That's going to allow us to Deshabu says, please, not the L298, I beg of you. So this is what's known as a H-bridge. So the reason it's called a H-bridge is because it looks like a H when you look at it on an electrical circuit diagram. So that's where it gets its name from. And it's quite interesting how this works kind of electronically. So to turn the motor one direction or the other, or even to speed up or slow down the motor, we can just use these 4 switches that we have. Now these switches that we see on this diagram here are in fact a combination of a diode and a transistor. So the electricity can only flow one direction, that's what the diode can help us with, and the transistor can essentially turn the circuit on or off, so it can allow electricity to flow through this. It's kind of an S shape, as I'll show you in a second. So we can either get the motor to spin one direction or the other simply by reversing the direction of the electricity that goes through this particular H-bridge. And we can control the speed of how fast the motor turns by essentially turning this on and off very, very fast. So that's called pulse width modulation, PWM, and the shorter the pulse is, the quicker the motor turns. If we get them turning off almost so it's imperceptible, that'll be kind of the 100% power, whereas if we leave a really long gap between turning them on and off, it'll be like 5 to 10% of power. So this is how it works. S4 and S1 have just now closed. The electricity can now snake its way through our motor up to the VCC, and then it can spin round. So if we were to flip those switches so that 1 and 3 were enabled, the motor would spin in the opposite direction. So that's how this works behind the scenes. And these pairs of switches essentially is just what that input 1 and input 2 will be on our L298N board. We'll have a look at that in code in a second. So we can control this by switching these switches high to low. Each motor needs a pair of these switches. Like I said, they're called input 1, input 2, input 3 and input 4 if you've got a second motor. And we can set these to high or low to control the direction of the motor. And we can also use this enabling pin, which we have on these ones, which is the very end pins. We need to enable them to make the circuit enact what we're asking it to do. So you can see there, if we have iron 1 as high, iron 2 as low, that makes the motor spin in a forwards direction. If we reverse that, so iron 1 was low and iron 2 was high, then it'll turn backwards. And if we have both of them as low, then it will essentially stop the motor. Now our Raspberry Pi Pico, it actually has 40 pins. So we'll be talking about pins. If you're new to electronics and robotics, you'll hear pins talked about a lot. And a particular type of pin is called a GPIO pin. It stands for General Purpose Input-Output Pins. Now the Raspberry Pi Pico has 26 of these. If you use something like an Arduino, that's got I think slightly less pins on it. It has 13 GPIO pins on it. And if you have an Arduino Mega, you can get a lot more pins on that. If you've got the Arduino Nano, I think it has a similar kind of number. So we have 9 ground pins. So on this particular diagram, the black GND, that stands for ground, and we have 9 of them. So there's 8 on each side. There's also another one at the bottom for the debug pins. The pins themselves output 3 volts, or 3.3 volts. And we can actually have a 3.3 feed if we want to take power from our Raspberry Pi Pico. Pin 36 on the top right there, that's the one that's coloured in red. That's actually an output pin of 3.3 volts. But when we enable our pin high, it actually outputs 3.3 volts. If we make the pin low from a digital perspective, it essentially outputs 0 volts, or as close to 0 as matters. So we can use that to control our motor driver board. If we hook up the wires between some pins and the input pins and the enabling pins down here, we just connect some jumper cables, we can actually make these motors turn on and off. We'll be doing that in the demo in a second. Now we have the line sensors. So this one I think is called the TCRT 5000. There's about 2 different varieties. Some have them pointing down, some have them pointing up, but they essentially work in the same way. This one just has 3 pins at the end there. These are quite cheap to buy. You can usually buy them in bulk. You get maybe 10 for a couple of dollars there. And this is a reflective optical sensor. So it uses infrared. It has, they look like there's 2 bulbs on there, but one's actually a infrared transmitter. The other one is an infrared photo transistor, so it can actually see the light. And what we do on here is we send out a pulse of light, and then we check on the other one, can we see that pulse of light? If there's something reflecting it and it's quite close, then we can actually detect that there's something that's very close, and we can see is it light or dark by the reflectivity. So we can use that in a minute on a line following track. I'll show you that. And we can actually detect and track a line. We can actually make our robot move forwards and track a black line on a white piece of paper. So it's quite a cool project to do. So we can attach this TCRT 5000 to our BurgerBot. I've made one of these already. If I just lift this up here. So this is my BurgerBot, and it has this extra sensor on the bottom, which is that line sensor. You can just see it there. We've got 3 cables, and they simply connect up into the Raspberry Pi Pico, which is just on the back of the device there. We'll have a play with that on the demo as well in a second. It's just held on with a couple of M3 screws, as you can see there. So it just connects underneath the bottom of the BurgerBot. So if you want to connect up the sensor, it's just got 3 pins. The 3 pins are the voltage pin in the middle, the ground pin on the left, and we have the signal pin, which is where we receive the information. Is it a 0? Is it a 1? Is there a line? Is there not a line underneath? Now it does actually have a little potentiometer in the middle there as well. You can see that little blue with a little white X in there. You can put a screwdriver in there and tweak it to bring up or bring down the sensitivity of the height, probably the best way to describe that. So the way that we can wire this up then, we simply just need to take that 3.3 volt feed from pin 36 that we talked about before. We can take a ground feed from one of our 9 ground pins, and then we can put the signal pin onto a Raspberry Pi Pico pin. So on this one it's pin 17. Not sure which pin I've used. I think I've actually used pin 17 on my actual project as well, so that ties up nicely. So if you like what I do and you want me to make more of these kinds of videos, do drop this video a like. Let me know in the comments if you have any projects on the go, any robotics projects. Be very interested to know what you're working on. And if you've not subscribed to the channel, please subscribe. It's the main reason I do these things, is just to get the subscribe numbers. That's all I'm about. So yeah, they'll be really appreciated if you do that. I do go live every single Sunday at 7 o'clock British summertime. It's what we're in now. So 7 o'clock you can join the show and you can ask some questions at the end of the show. Right, let's have a bit of a demo, shall we? So I'm just going to get my Thonny open. I'm going to make sure we've got a robot plugged in, and I'm also going to go over to our overhead shot. So I've got this kind of skeletal BurgerBot here. It's not got any motors on it, but it has got a rangefinder just there. And it also has the Raspberry Pi Pico just here, which is plugged into my Mac, which is the code I'll be running in a second. I've also got this little motor plugged in to motor A on a little L298. N board. We've got some power coming in from my desk power supply, and we also have some pins going out to our Pico there. So what I'm going to do, I'm going to write some code. I'm going to write some code just on the screen first, and then we'll come back to show you how this actually works. So let me just get my code up on my other screen so I can see what I'm typing. Right, so the first thing we need to do is from our machine, we need to import pin, because we're going to be setting up some GPIO pins, and something that's called, let me make sure I get the right code before I start typing all that in, DC motor, there we go. And let's bring in pins poorly defined for now. Let's do from machine, from time import sleep. Sleep helps us pause if we need to do something that's time sensitive, and a lot of sensors and motors we need to use the time function for basic kind of timing. So the first thing we need to do is set up our GPIO pins to tell them that there's going to be a motor attached to this. So what we need to do is just put a little comment, that little pound sign there, hash sign if you're in the UK. So we're going to say motor control pins. Okay, so IN1 is going to be equal to a pin, and this is going to be on pin 16 for this particular setup. That's what I've got it wired to on the Raspberry Pi Pico. And then we need to tell it that this is an output pin, so it's outputting digital signals rather than listening to them in. We then need to do IN2. This is going to be on pin 17. This is also going to be a pin.out for an output pin. And then finally we've got the enabling pin, so the enable A pin, so that's going to be on pin 18. So they're all nicely next to each other, and this is also a pin output because we're just outputting values. Now we need to create some functions to make our robot go forwards and backwards, because we're going to be doing this quite a bit, and there's a couple of sequences of things we need to do to make our robot go forward. So we use this define function word. What's it called? Like a reserved word. Oops. And what we're going to do down here then is type in motor forward. So this is a function. When I press return at the end of the function, it knows to indent it. That's a part of Python that we need to remember. So I'm just going to do a little print function here. This is just going to say forward. It's just going to print it out to the console that we're moving forward. And then to actually make the robot go forwards, we need to set that IN pin 1 to high. So high is a special reserved word, and IN2 needs to be low. That will make the motor go forward. We also need to make sure that enabling pin is set to high as well. Now, if we were to run this code and do motor forward, this code will actually tell the motor drive board to indeed make the motor go forwards, but we need some way of telling the robot to stop. We need to tell the motor controller board to stop at some point. So we need another function which is simply, let's call it motor stop, like so. And this one is going to do the same thing as before, which is just going to print out a little message, oops, that says stop. And then we're going to do IN1 low, IN2 low, and enable 1 is also going to be low. That will basically stop the motor from spinning completely. Now if we want to make the robot go backwards, we can do motor backward. Let's do motor backward, and we can do print again with backward. And the print statements just help us as if we've not got things wired up, we can see that the command is being fired, if you like, because the code is actually printing out the word forward, stop, or backwards, depending on what sequence we run these functions in. And we should also see the motor turn round as well. But if it doesn't turn round, we know that the code is actually firing. It must be some kind of electrical issue. So for backwards, we now just need to do IN1 to low. So it's essentially the opposite what we had before. IN2 is going to be high, and then EN1 is also going to be high. Okay, and we now need to write little test code. So let's call this one a test comment down here. So I'm going to say motor forward, then we're going to sleep for so many seconds. So let's sleep for 2 seconds, Then we'll do motor backwards. That's going to be another sleep for 2 seconds. And then we're going to say motor stop. Okay, right. So I'm just going to run this to make sure I've got no typos or anything, and then I'm going to check and see is everything as it should be. So I can see that that's actually not running. So let me see very quickly what I've done wrong there. It's got pin 16 pin out, pin 17, and then 18. That's the issue. Right, so if I run that now, yes, that's working. Okay, so what I'll do now, I'm just going to go over to this kind of split view, so you can actually see when I hit the play button on our code, you'll be able to see the console, and you'll also be able to see this little motor here. So I'll just hold it up so you can see when I hit. So that's forwards, it's then going to go backwards, and then it's going to stop. So if I run that again, forwards, backwards, and then stop. So if we were to build a robot with this, we would actually need quite a large robot because this board is physically quite large. So probably something a bit like this kind of robot, this kit. I think I bought this one on Amazon. It really wasn't very expensive. It came with 2 of these TT motors, I think they're called. They don't actually have any cables on them, so you'd actually have to wire the 2 cables for the motor. And it came with a battery box as well, so you can put 4 AA batteries in there, and that should give you 6 volts. You could plug that into the Raspberry Pi Pico. It's a little bit more than it would normally like, but it can actually drop that down safely. So we can power our robot, both the motors, the motor driver, and the Pico itself from that little battery pack there. And typically what we'd do, we'd put on some kind of like breadboard, and we'd probably also put the motor driver on there as well, so we can physically fit these on, but you can see it's quite chunky. We'd also need somewhere to put the microcontroller on there as well. So when I've built other robots, I've used much smaller boards. In fact, I'm going to spin around and get the other board I built over here. So this robot is another BurgerBot, and you can see this one has the MX1508 board. It's kind of floating on some cables. The intention was that this would actually sit flush on the PCB that I've got there. You can see what the PCB, you can see what the rangefinder that plugs basically into the PCB, and we've also got the microcontroller, the Pico there as well. The motors simply plug into some connectors either side, and they then get routed through the motor control board. But it works, the code would be exactly the same to control this robot, but you can see it's much smaller than the larger one, so it can literally fit on it. It's that much smaller. So if you want to go small, you can use much smaller motor control boards. Okay, so that's how we can make a motor go backwards and forwards and stop. That's one of the most fundamental building blocks of our robotics. So let me now look and see what we're going to be covering off next. So we've done that, we've looked through the different motor controller boards. Let's now have a look at the line follower. Line following is one of the fun projects that you can do in robotics. I'm just going to go to the overhead for a second and just wire up this next robot. So this one uses combination of different boards on here. So I've got a Raspberry Pi Pico just there. On top of that there is a motor shim from Pimroni, and that enables me to control these 2 motors very simply from some other cables which are just inside there. So there's 2 little, quite difficult to show you this on camera, 2 little white cables there. One goes to the left and one goes to the right. But that motor driver that's in there works in exactly the same way as the other ones that we've just looked at. This also has a little LiPo battery that powers the robot, and we can simply turn that on and off using this little button that's just on there. But because I'm powering this through this cable here, we're actually not going to play with the motors too much on this one. This is more about the line sensor. So you can see what the line sensor there. There's the this is the slightly different variety that's got the, if you see the one I've got next to it, these 2 work in exactly the same ways, but this one has got like a little the photo sensor and the infrared transmitter point straight down, whereas this one, they kind of point that direction. So you'd have to hold this in that kind of orientation if you were to build it on here. And this is the kind of direction I wanted for this. So these cables get routed, they go to cables. Let's make sure this is correct. So that needs to go to pin. Yeah, and see we've got power there. So we've got ground, we have a signal, and we also have the 3.3 volts, which is just this cable here. And what I'm going to do is I'm going to make this go across this this black line, and I can see there's a very, very faint, if I turn off the studio lights for a second, there's like a little red glow from the sensor that's just there. Can you see there's like a very small LED, and that tells me when I'm over the black line or not. So the sensor is now over the black line, the light's gone out telling me that it's detected that there is a light there. But let's do this in code. Let's have a look and see what this actually looks like. So what I'm going to do, I'm going to go back to Thonic. We're going to open up a new one, which is the line follower. And let's get my code on my other screen. Try and make less typos. It's really, really simple, this code, because we're simply just looking to see, is it a 1 or a 0 that's coming from the line sensor. So from machine import pin, once again, from time import sleep, and then we're going to say the sensor input pin, and that's going to be sensor equals pin. We're on pin 17, and this time the pin is going to be an input pin, so it's not an output. We're looking to get data from the sensor. So now we have a loop which says while true, and we say if the sensor dot value equals 1, so we have the double equals because we're comparing the value that the sensor has with this value here, which is number 1. So if it is 1, then we can say print line detected. Oops. Else, if it's a 0, but we don't actually have to say that, because if it's not a 1, we can say any other value. We want to say print no line. Okay, and then so that this doesn't just spit out thousands of things on the console, we can actually just give a bit of a delay. So we'll do 0.1 of a second on there. Right, that's all we need for this code. If we now just do stop and then start on here, you can see it says no line. And if I now move this, if I go over here and I start moving this, so it's on the camera there so you can see, let's move the sensor so it's detected a line. If I move that a bit further, there's no line. If I move that back over the black line, you'll get to see where the line is. There you go, line detected. And if we go past that, we get no line again. So that's the thickness of the line just there. So we can actually use this in combination with some code to make the robot drive forward. So we can say drive forward. So if the robot drove forward and then it detects that there's either a line or no line. So when it's detected a line, we can make it go forwards, and it'll go all the way until it gets to some kind of corner. I'm going to show you this on it. Right. So we've got a corner there. As it approaches the corner, get that over there. So we've got a line detected, and at some point it's going to say no line. So at that point we could have some code that says turn the robot to the left until line's detected, and then go forward and then no line, so turn to the left, and it'll keep doing that until it detects the line. So we can have code that says if you don't detect a line, turn left ever so slightly and go forwards. If you detect a line, continue to go forwards. So we can make a line following robot with just one of these line following sensors, and that means that it's really easy then to track the line. Now for better quality, if you have an array of these, I'm just looking to see where I put the other robot can't see where I put that one. The Arduino Alvic robot, I think I put it away somewhere. That one has a number of sensors on it. I think that's about 3 different line sensors. So you can have one that's tracking that there is a line detected, and the other 2 either side should detect no line. And if it should detect that there's a line on 2 of them, you know you need to sort of correct and turn to the right, and so on. So yes, Dale's just said that ideally you'd have 3 sensors for left, centre and right, and then you can tell which direction to turn accurately. And you'll find that your robot has less kind of wiggling and it's more accurate. You do tend to need to go slow as well when you have a line following robot. It's quite tricky to detect lines if you're moving very, very fast. So that's how we do a line sensor. And the other sensor that's very, very common on robots, which I have, if we go back to this one, this is a rangefinder. So if I just hold this up, a lot of my robots have these little rangefinders that look like eyes. That gives your robot a little face. So what we'll do, we'll just pull the cable from that line following robot. Interestingly, that line following robot has a different type of sensor on there. That's actually a camera. So that sensor there is a ESP32 camera, and that means we can actually get a video feed from that one completely independently of any of the rest of the electronics. Right, let's plug back in our first robot. Just going to move all the stuff out of the way there so that we've got a nice clear run for the sensor there. So let's go back to our code and create some line sensing code. So not line sensing, range finding code. Right, so this is going to be our range finder. Now rangefinders use ultrasound. You can get ones that use laser time of flight, but these are the most simplest ones, and they're also quite cheap as well. So let me just pull the code up for that one, and you can code along with me. This one also is quite a short program. So from machine, guess what we're going to do? We're going to import pin, and we're also going to import something that's called time pulse US. So US is microseconds. These are very, very short periods of time indeed. We're also going to do from time import sleep. And we're going to have 2 pins on our rangefinder. There's a trigger pin. So this is going to be on pin 1. And this is a pin that's an output pin. And then we're going to have the echo pin. And this is where we listen. So the trigger essentially spits out a sound. I think it's like 40 kilohertz, so 40,000 hertz. It pings out an ultrasonic blast that will bounce off an object and come straight back at the sensor, and we can listen for that using the echo. So the echo is a little microphone, a little ultrasonic microphone. I'll tell you about other ultrasonic things if I remember in a minute. So we need a new function which is get distance. And this is going to, first of all, set the trigger to low. We're then going to sleep for a very short amount of time, so 0.0002. Then we're going to set the trigger to high. Now setting the trigger to high will make it pulse out some ultrasound. It doesn't matter really how long we send the signal out for. What we're going to listen for is how long it takes to come back to the echo. So we're going to sleep again. So this time we're going to sleep for 0.01, so a hundredth of a second is that. And then we're going to say trigger is low. So the duration is going to be equal to the time pulse microseconds. So we're going to pass in the echo pin, we're going to pass in 1, and then we're going to pass in 30,000. The 30,000 is the timeout, 30 milliseconds. And then the distance in centimeters is going to be equal to the duration divided by 58. So why 58? Interested to know if anybody in the chat knows why that might be. And then we're going to return what the distance is. That's really what this function is all about. Right, so now we can say while true, and we can say distance equals get distance. We can then print to the console distance. Now you can do this a number of different ways. I'm going to do this the simplest way first of all in this print statement, then I'll show you a slightly better way. So dist and then centimeters, and then we can say sleep for half a second. Now to me that looks a bit messy. We've got the word distance, which is a string, then we've got a variable, and then we've got another string. Now what you can do instead, you can use an F string. So if we put F at the beginning there, we can actually get rid of that first speech marks. We can enclose this in some curly braces, and F strings are smart enough to know that that means that this is a variable, and to swap that value with the actual value of the variable that's been passed in. So that's an F string. I just think they look a little bit neater. Right, so what I'm going to do, I'm going to run this. I'm going to first of all hit stop, and then I'm going to, have I got that plugged in? Let me just make sure we're all good. I have had it do this a few times before. I find if you just flick over to a different one, or just plug it back in. I can actually turn the power off as well now, because we don't need the motors on anymore. And there we go. Right, so if I now run the code, I've got a bit of a typo there, so true should be in uppercase, capital case, like that. There we go. Right, okay. So what I'm going to do, I'm going to get this lined up on the desk so that you can actually see. Let's get something. I've got a little Raspberry Pi box here. This is a Raspberry Pi Zero box. I'm going to hold this in front of our sensor. I'm going to just remove some other bits and bobs from here because we don't need them anymore. They're kind of getting in the way, obstructing a little bit. Right. So if I hold this box at a fixed distance, let's see there. So this is about 20 or 30 centimeters. I'm going to move this closer now, and let's see that distance drop. So it's now saying 15, 14, 12, 10, and you'll see on the camera there, we'll go about 5, 6, 7 centimeters. If I keep going even closer, 3 centimeters. There's a point where it can't accurately guess the distance because the microphone and the microphone and the speaker are further apart than it is close. So there you go. 2 is probably about the accurate distance it can measure there. Now the other thing that's a little bit unsatisfying is that the distance has got all these decimal points, and we only really want to have probably at best 2 decimal places. So we can actually use the rounding function if we wanted to round this down. So let's have a look at how we might do that in our code. We could, if we wanted to, if we didn't want any decimal places at all, we could use the double slash. So if I run that code now, it'll just be an integer, a whole number. So if I now move this, we can see that this is 9, this is 6, 7, 5. If I move that completely away, we should then, once it's caught up, because we're taking measurements and there's a little bit of a lag, you can see that it's detecting, I think, the arm of the camera that's just on the desk. If I move that out of the way, can we get an even further measurement? Let's see. There we go. And I believe it can measure up to about 3 meters. But my chair is actually in the way. There we go. So we've got 300 centimeters. If I move my chair out the way, let's see if we can get it to do that again. Maybe if I move out the way. It's quite tricky to actually. There we go. We eventually got there. And we can put our hand as well. That's another nice easy one. So we could use this to make our robot avoid obstacles. If there's an obstacle that's less than 10 centimeters in front of the robot, we can make the robot stop and then turn, and then we could check again to see what's the distance now. And only if that distance is more than 10 centimeters, we could then make the robot go forwards. So that'll be an obstacle avoidance. Now if we wanted to, we could make a following robot so that it always keeps a distance of 10 centimeters, for example, from the object. If the object's your hand, you could make it follow your hand. So it'll go forwards depending and try and keep that distance. So as long as it's between, say, 12 and 8 centimeters, it can maintain that distance. And you'll see the robot kind of catch up and or reverse back. It's quite a fun project to do that. So that's rangefinders. Now the only thing I need to say about rangefinders is there are two different types of ultrasonic rangefinder when you're looking online to buy these. I'm just going to pull this one out and I'm going to show you the on camera. So unplug that so it's going to give some wacky readings now. So if I hold this one up on the main camera and I show you the back of this, you'll see that it says, let's spin that the right way around. If you look on the right hand side there, it's got Echo TX SDA, and it also has Trigger RX SCL. And then at the very bottom it's got R4 I2C, and it also has R5 UART. Now that tells me that this is a 3.3 compatible ultrasonic rangefinder. There's a whole bunch of other ones which only work with 5 volts. Now they would work fine with an Uno or potentially a Raspberry Pi Pico 2 because they're 5 volt tolerant, but if you're using the original Pico or Pico W, you need to make sure you're using 3.3 volts only. Otherwise the ultrasonic rangefinder first of all won't work because the voltage you're giving it is too low, and the voltage it will try and give back, if you manage to feed it with 5 volts, it would actually send back 5 volts on the echo pin, and that would damage your Pico. So you definitely need to make sure you get the I think these are called HCSR04 or HCSR07, but they have like an L version for low power. So definitely check out one of those if you are building your own robot. So if you also want to get all the different measurements of these, if you're building a robot enclosure, such as this one here, you can see I can simply just push this rangefinder into place and the measurements are all perfect. They're actually from my Robot Maker's Almanac, which you can buy from the kezrobots.com store. So if I turn to, let me find the page that these are on. So I've got a little index here and it tells me the ultrasonic rangefinder. These are on page 30, so the dimensions are on page 30. So if I pull that here, you can see there we've got the ultrasonic rangefinder. The distance between the two center points is 25.5 millimeters, and the diameter of the round bit of the eye, if you like, is 17 millimeters. So all the different dimensions are on there. So you can get yourself one of these, and it just helps if you're actually building your own robots. Cool. So let me go back to my notes and see if there's anything else we needed to cover off on that one. So yes, I asked the question before, why 58 was used in that calculation of the rangefinder. So if you think about how rangefinders work, they're going to bounce a sound wave from the little speaker, and that's going to travel in time. It's going to hit some object, and then it's going to bounce back to our little sensor. So it's actually gone twice the distance. So we need to figure out, we only want half of that distance to get the distance of the object. We don't want the full transfer there and back. And the speed of sound, if we use a rough approximation, is 58. We can use that in our calculations. It's an approximation of the speed of sound in centimeters. So we can use that in our calculations to get kind of a rough and ready one. I've used different values in the past, but this was one that I came across. Okay, so let's get back to our slides. This is kind of part one, if you like, of this how-to tutorial. So if you want to join the Discord community, we have our own Discord server. It's free to join, and you can meet loads of people online who are all building robots as well, in the same kind of position that you will be in as well. So if you have any questions, it's probably better to ask those people rather than asking me directly. I get a lot of people emailing me or reaching out on instant messenger platforms asking for help directly. And I'm quite time poor during the week, so this is probably the best way to get answers. Cool. If you want to follow me on social media, I'm on all the different social media platforms. I'm at McAleer at threads.net. I'm at McAleer6 on TikTok, at Kev McAleer on Instagram, at KevsMac on X, and at KevsMac at Mastodon.social on Mastodon. Also on Blue Sky as well, at kevsmac.bsky.social as well. So if you want to follow me, you can head over to any of those platforms. Definitely say hi, and I'll say hi back, like you do. If you want to join me as well, you can get your name in the end credits. Simply go to kezrobots.com/coffee and you'll find all the different details there if you want to play along and help support the show. So at this point, I will hit this little button here. It's a little bear's paw. I don't know why I've stuck with that. And here are the people who have done exactly that over the past week or so. So we have some anonymous coffees. We've got an anonymous one there, and also somebody bought 3 coffees. Thank you both for that. We have another anonymous member. We've got Silicon Fiber, Marie TKD, we've got Andrew, Jeff, DN Corty, Marley, and Tom. They're all in the Buy Me a Coffee membership. And then on the YouTube side, to do it the opposite direction, we've got Dale, we have Pierre, Pierre Eves, we've got Charlie, Oxrad39, Bert, Marie, Michael, Steve, Ford, Bello, Littleback, Paul, Johnny, Stephen, John Paul, Cassie, Tinkering, Rocks, Johnny Bates, and of course we have Tom. Thank you all for supporting the show. It means so much to me that you continue to do that. And who do we have this week celebrating? Was it 13 months of being a member? So yes, Johnny has been a member for 13 months. So congratulations on that. And thank you for standing by me. I really, really do appreciate that. Cool. So I'm going to head back to my little slides there. And yes, we've done the supporters one. So that little spinny logo tells me it's at this point in the video where YouTube will recommend over here a video for you to watch from the over 420, I think it is, videos I have in the back catalogue. So definitely check one of those out, and you'll also be supporting the channel by doing that too. So at this point in the video, I'll say thank you so much for watching, and I shall see you next time. Bye for now. And I'll just hit the stream marker button there, and we'll have a quick look and see what people have been talking about in the live chat. So let me scroll up over here. Lots of talk. Oh, there's some cooking tips there. Marie asked Ford for any cooking tips, and Ford has come through with those. Yep, pre-made cookie dough is much less worse than homemade. Much less worse. Oh, much less work. I thought that was much less worse. Much less work. I remember when I was a kid, we used to have like, my mum would make a cake, and the cake mix, which is just like flour, sugar, egg, and maybe milk, whipped up, and it just tastes the nicest thing ever. So I remember thinking, like, when I grow up, I'm going to make a cake mixture and then just eat the cake mixture, not actually bake the cake. Never actually done that yet. probably for good reason. So Ford said, I started buying pre-made chocolate chip cookie dough in recent times because I didn't have the energy to make homemade cookies. And hey, it makes a quick dessert. Keeps a while longer than homemade too. Yeah, it's probably got some preservative in there that helps with that. So Alex says, I would struggle not to eat the cookie dough raw though. Exactly. So Dale says, Pimron is out of stock of the N20 motors with the encoders. Yeah, they go through kind of periods of that because they have to manufacture them in house. They get the N20 motors in, and then they have to attach the little encoder circuitry. I think they've got like a machine that helps them do that. So if you send the support team a message, I'm sure they'll bump that up the production list. Phil says, I mean, I like little blobs of cookie into my mouth while scooping it out. Yeah, and the separate encoders as well. So yeah, they have to get those made. They have to get the PCBs made, and then they have to put them into the big. They have like a great big pick and place machine. It's a really beautiful machine to watch in action. It's just so fast, but you've got to prepare the little PCBs. You've got to scrape on the solder paste, and then put them into the little conveyor belt, and then it'll go along, and the pick and place machine will do the rest after you've put in the right components, of course. So there's a whole piece there. So now here in America, edible cookie dough is something you can buy. Alex says, yep, they sell it here too. It tends to be way more expensive than just buying more cookie dough though. Cool. And thanks for that, Dale. Appreciate the help there. Alex says, but you've never had Angel Delight. I had it the other day. I don't know if it's an inherently British thing. Never had Angel Delight. It's like powder. It's like a powder you mix milk into, and it makes kind of a mousse sort of cold dessert. Yep. I remember we used to have that when I was little. You can get strawberry or chocolate. I've never seen it anywhere here in America. The closest thing was Jello pudding mixes. So Deshpu, tell me why the hatred of the L298N? What's the issue there? Alex says it was a school canteen dessert that was really popular. I don't think about edible cookie dough. Really going on a cookie dough theme today, aren't we? Pillsbury's cookie dough can be eaten raw. What's wrong with it? Makes me laugh as I have no idea about this at all. Yep, so when we go to San Francisco, we'll pack a bit of a care package, Alex, of all these things. We went to, is it a Trader Joe's? They had like loads of interesting stuff in there. It's a refrigerated item. Yep, probably not then. Kimmy brings loads of cool bags. So actually, we shipped over loads of robot stuff for open source last year, and then we also sent it back, and it got back home in about a day. Like, they do not mess about. I think that was a FedEx. So yeah, they really don't mess about. Get some cool bags, lots of frozen gel packs in it. Costco stocks it, I can get it. It's an ancient part designed to work with 40 volt motors with the voltage dropped on it like it was 2 volts. Yep. A lot of these parts are very common, but they're also quite old. I know there's like a desire to use these much smaller motor drivers now. I think this has actually got a better spec than the and by better spec I mean it can handle like higher voltage loads, but like look at the size of it. How can it? And then you look at this thing with this great big heat sink. I see heat sinks and I just think wasted energy, because like it's just converting any energy it doesn't use into heat to try and drop the voltage down. So that means just use a better voltage in the first place. There you go. Dipu says modern motor drivers are much more efficient and still work with 3.3 logic without the need for level shifters. You see, exactly that. By Kevin a cup. Oops, I mean coffee. Yeah, I think it did freeze a little bit early on in the video. I noticed there's a bit of a spike. It's a live show, sometimes that can happen. Hey Marlene, how's it going? BattleBots, absolutely. 18 when he's typing 19, and that's why it didn't work the very first time we tried it. Dell says I would have done iron 1 and EN1 equals pin 16, 17, and then iron 2, EN2 pins 18 and 19. You did not define EN2. It's because we're only going for one motor on that particular one, and then sure enough, nailed it. Yep, you spot it. It must be really frustrating when you watch me do typos and I've not spotted it. So Dale says, ideally we would have 3 sensors, yep, left, centre and right for the detections. Yeah, I think we covered that, didn't we? Hey, Frankie Boy Power Care, how's it going? I go for a damn joke, really. And Goldfinger says, question, if you want your motor to move in small movements, could you use a continuous servo instead of a motor? That's a great question. So yeah, continuous servos work differently than motors. That, like electronically speaking, they've got a little controller board inside the servo. If you've ever like cracked a servo open, you can see inside this. In fact, I think I had a slide on that. Let me see if I've still got that open. I literally had a slide on that open a couple of seconds ago when I was putting my show notes together, so I've probably got it. There we go. How do servos work? I'll just flash this up. So how do servos work? So inside the little box, if we were to sort of strip that away, you've got the DC motor, you've got the gearing, you've got a little potentiometer. Now the continuous ones, I don't think they have the potentiometer in there. They have like an encoder instead, and they have this little control circuit, and this is the thing that receives in that pulse width and matches up the motor with the potentiometer, so it figures out what angle it should be at. But in the continuous ones you don't have that. It has like a different kind of thing, probably an encoder. So with regular servos they use pulse width modulation, so these are the pulses. If the pulses are like really, really small, then it's going to be, basically if there's not very much power being provided, the motor's going to turn slow. if you provide lots of power, so there's more of a pulse and less of a dip, then like the duty cycles more, then you can have more power going to your motor, and therefore it'll turn quicker. So that's the thing I just wanted to share there. So yes, you could do that. You can also just have more of a, you can just dial down the power. So rather than having on or off, you can use pulse width modulation, PWM, on one of the pins, and therefore it'll be, you can use the PWM values to provide less power or more power. I'll cover that in a different show, because that's probably quite a good question, that one. Welcome to the Cookie Dough Show. Next time I'll talk about how to make your own Oreo cream. Fascinated the responsive BattleBots. I'm fascinated how responsive BattleBots are to their controllers. Yeah, I mean, robots are pretty responsive. These microcontroller boards, motor controller boards, they can work. What am I trying to say? They can send signals to your motors like in real time. So you can make your motors, if you've got like really powerful motors. I've actually got some really powerful motors down here. This is one on a project I'm working on, and you can see this has actually got the encoder on the back. So that's why it's got all these cables. There's basically the plus and the minus, and also the encoder cables as well. So I need a special kind of controller board to control this one. But yeah, this means that this can, with sufficient power, this can move the robot really rapidly backwards and forwards. But yeah, those things really move around fast, don't they? Yep, no problem, Ford. Thanks for that. Thanks, Dale. Great. So I think that's everything I've got to cover off this week. There'll be no show next week because I'll be at Maker Central in Birmingham, NEC, for the Maker Central event. So that's across 2 days, Saturday and Sunday. Unfortunately, it's just far enough away from where I live that I can't prepare a show and then present the show. I'll be still travelling at this time. So I'll be back the week after. And yeah, I shall see you then. Thanks for watching. Bye for now. Presses the wrong button.